Vou variar, eu não consigo fazer sempre a mesma coisa.
E acho que vai ser também.
So we switched to English because of Egino. And so to get started with this class, perhaps I will do a brief overview of what ROS is going to do. Let me just put here PSR and well, share. Okay. So we are going to work on exercise number 6. Not here, I'm in the wrong part. Part 11. Exercise number 6. So what we have in exercise number 6? We have a SCADA robot. So a SCADA is a special type of robot which moves only in the ZOY plane, so Z equals 0 plane. And you have major manufacturers, world manufacturers, international manufacturers, developing this kind of robots, okay? So we are going to do this because this is a more simple kinematics than a 6 degrees of freedom manipulator. And it's just for you to learn how it works. So the idea is that we have a SCADA robot like this. I've just drawn some stuff here. And the goal is to try to develop a system, a description for this robot in ROS, so that we can move everything, okay? So let me first perhaps bring this. Okay, so first, let's try to figure out how ROS works on this, how robots are represented and so on and so forth. Okay. And now new PSR. Ora, hoje são 15, 12, 22, okay. Okay, so first thing, let's put here the image from the exercise. Done. And we can even increase this. Okay, so this is our starting point. And what we want is to define 1, 2, 3, 4 links. So the base link, link 1, link 2, and the EE link, that stands for end effector link. End effector is the end of a manipulator. And people from the robotics course, from the other robotics course, Robotic Industrial, they know how to do this. This is called direct kinematics. So basically, what you have is a set of coordinate systems, and you have what are called the geometric transformations. The geometric transformations between one link, let's call it link 1, and another link 2. These are coordinate frames that is read. Transformation from L1 to L2. And you know how this is. It contains a 3x3. So this is a 4x4 matrix. It contains a 3x3 rotation. So the rotation component is a 3x3 matrix. Then you have here the translation component, which is a 3x1. And then you have the homogenization of the matrix, which is 0, 0, 0, 1. That's the standard geometric transformation in homogeneous format. And if you want now to compute a transformation, for example, between the base link and the end effector link, so I would have to do something like this. The transformation from the base link to the end effector would be the transformation from the base, better still, transformation from the base, okay, from the, so the base is connected to the link 1, so L1, then the transformation between L1 and L2, and finally the transformation between L2 and EE, end effector, okay? So when you have a chain of geometrical transformations, what you have to do is to compute the aggregate transformation by multiplying the partial transformations in proper order according to the topology of the chain, of the kinematics chain. Now, if you look at these transformations, you can see that some of these transformations are dynamic, whereas some others are static. So, for example, the transformation, so from L1 to the base will rotate. That one will also rotate. Yeah, in this case, no transformation is static. So all of them are dynamic, which means that this and these transformations here will vary in accordance to the joint values. What does it mean? It means, for example, that the transformation between the first link and the base, which is this one, okay? So this is the transformation between the base and L1, will be something similar to this general equation that I've written here, and it will contain some values in rotation and translation. In particular, the values of the rotation will be dependent, will be a function. The rotation will be a function of the angles, let's call them J for joints. So you have joint angles. In this case, we are talking about this angle here. This angle will define what is the rotation matrix, right? So if you want to consider it, think of it in a different way, you can say something like this. Transformation from the base to the end effector is going to be a set of transformations which are produttorio, got it. So this means the product of some transformations between some links and some others, let's call them link A to B, and these links are a function of joint angles, okay? So now let's think about ROS. So I could go on for another half hour because, but you should see the video. So I don't want to overlap with the video. Yeah. What would be an example? Yeah. So here's an example. Oh, my color went wrong. So here's an example. Suppose that I have here my world coordinate frame, just because I want to. And then I have a transformation between the world and the base of the robot, which is static because the robot is screwed to a table or something like that, okay? So this transformation will not depend on the joints because it's a fixed transformation. And there are many examples in robotic systems of fixed transformation. Typically, it's a combination of fixed and dynamic ones. Now, how about ROS? That's what I'm looking for. This point here was very important because it helps you to understand what you are doing in ROS. So in ROS, if you want to do this, you will need to draw. Let's go from the end to the beginning. So in RVs, what you really want to see is something like this. This is my robot. There is another link here. And then there's something else there. Okay? This is what you are seeing in RVs. This is what you want to see. So basically, what RVs is doing is drawing all of these bodies into the same coordinate system. The fixed frame that you select on RVs, fixed frame, that's where you decide on which coordinate system, all the bodies will be drawn. You cannot draw one body on one coordinate system and then another body on the different coordinate system. It doesn't make sense. All of them must be drawn in the same coordinate system. Same coordinate system, right? So when Arvis receives these bodies, it will receive, let me change the color to green. Let's say that one is green. So what Arvis actually receives is the green body, the red body, and the blue body. And it needs to put them into a single coordinate system. Let's say the coordinate system of the blue body. So it will have to, if we select, for example, for the fixed frame, the blue, we will need to be able to find a transformation between the red and the blue in order to be able to draw the blue, and the transformation between the green and the blue in order to be able to draw the green in the blue's coordinate system, right? So if you want to think of a TF3, what we have is something like this. In a TF3, transformations as we've studied them this morning. So this is the base link. This is link 1. This is link 2. And this is the end effector. Okay, now what I'm saying is that I need these transformations which are the edges between these systems. That's how I can draw everything. So, again.
This would be reference of the green one to the red one.
Yeah, well, yes. Well, when we define from the red to the green. That's when we are configuring. But then we can ask Ross to tell us directly from the green to the blue. We define from the Earth to the moon, but then we ask from Venus to the moon, right? Okay, so how do we get these transformations? We get them using a node called, so these are TFs, okay? So these are transformations in Ross RTFs. And we get them by using something called robot state publisher. So it publishes the state of the robot, which means it publishes the transformations between the components of the robot. So robot state publisher will output the transformations that Arvis is waiting for. Okay? Now, what will the robot state publisher need in order to compute the transformations? You guys that are doing manipulator robotics, you know what you need is a model of the system. So you need to know how the system is arranged topologically. For example, if you are doing the direct kinematics of a SCADA robot or a 6 degrees of freedom manipulator, it's different. The equations vary. So Ross does something very nice, which is from a new RDF description.
What we're going to add in the
Similarly, it derives the DH, the Danapi-Tattenberg parameters from the URDF. All right. So from the URDF, you will feed it. Well, let me first do all the steps. So you have your URDF file, and you will load a Ross parameter, Ross param, called robot description. So this Ross parameter called robot description is read after the URDF and then is read by the robot state publisher. So robot state publisher will derive the Danapi-Tattenberg kinematics from there. And this is nice because it's the general Danapi-Tattenberg kinematics. It is general in the sense that you can define whatever robot you want, and it will automatically generate the DH parameters. And then in order to compute the transformations, you still need something else, which is the value for the angles of the joints. So it will still need to receive something like what is called joint state message or joint states. Okay. Joint states are the values of the joints. Now, with regards to the joint states, if we were connected to a real robot, what we would do is we would connect to some robot driver, which would read the position of the joints of each angle and publish in the ROS ecosystem. We don't have any of that right now because this is all simulated. So we are going to create a interface which will take a look at how many. So this interface is called joint state publisher, GUI. It will read from the URDF in order to figure out how many dynamic transformations we have. And now it will take a look and see, okay, so we have 1, 2, 3 dynamic transformations. So it will say, for joint 1, here, tell me what is the proper value. And for joint 2, tell me what is the proper value. Okay. So this application will now publish the joint states, which are given to the robot state publisher, after which it can finally compute the transformations that RVs uses, okay? So this sounds a bit complicated, complex, because this is not straightforward, but it's really, really powerful because it's modular. You can use, for example, as I told you, I can take away the joint state publisher GUI and put a real robot or the gazebo simulation. So this works very nice, this pipeline. And all these exercises that we have. Yes, it will be the controller of the robot. So what does the controller of a robot does? It will read periodically the encoders and figure out what is the angle of the joints. Yeah, the GUI is something that will let you define the value. If it was a real robot controller, you wouldn't define the value, you would just be reading it. By another control loop, with which you will tell the control, okay, now move. But it's a different control loop. One of them is just reading the position and feeding it to the joint states, which then goes into the robot state publisher. This is just unidirectional. Then there is another control loop, yeah, to move. Right, so I think that's it. Now, why did I want to tell you about this? So that you don't get puzzled when I tell you that we must read the URDF file, launch the joint state publisher and the robot state publisher, and so on and so forth, okay? So now, let's go into the code. Well, before I go into the code, I will give you half an hour until 2 o'clock in order to try to do the exercise. So, look. What I've been telling you now is what is here on exercise 6. That's the creation of the URDF. Exercise 7, that's how to launch the robot state publisher and the joint state publisher. And then you have here on exercise 8, also how you can put this in a launch file and how you can launch RVs, okay? So all these ingredients are actually on exercises 6 through 9. So I will give you half an hour, 35 minutes to try to do it. And then I can do it myself or ask someone to show how it went, okay? Okay. Você não tem problema de falar? Esse valor é escrito como assim. Não diria que são. Vou passar para o tempo. Passar para o tempo, já vai passar para o tempo. Está aprendendo depois dela, porque eles passam a primeira mão. Vou instalar o grupo de editores, mas no final quer ser. Não vai estar? Ok. Não lembro como é que se dela o package. Como é que se chama o package? Era cá que está a package depois o sítio. Olha, não sei. Google. É o que eu faço. Coloca o package. Coloca aqui o package. Isso para cá também. Isso. Já que isso tem que ir ao Paga e eu volto a criar. Mas estava lá, dizia lá no...
Estava, eu queria escrever.
Não fez copy-paste.
Mas aquilo era brincadeira de vitória.
Trocava só essa parte. E não se esqueça de pôr também vezes do TF. Talvez seja preciso, não tenho certeza.
Nosso pai, nosso secretário.
Vai para o STP, std_mscs e TF.
Se quer marcas como o vosso quer marcas, talvez não vai ter um marca.
Ah, ok. Sabe que eu não sou muito curioso. Eu, quando tenho uma receita que funciona, não vou... É que não tenho tempo para experimentar coisas alternativas. É. Já contei a história que uma vez pediram para mudar uma coisa numa formação de ROS e eu mudei. Olha, quero exatamente não pôr as dependências. Ah, não podes pôr as dependências depois? Posso. Então porquê que pões sempre? Ah, pá, funciona. Ah, mas podes não pôr? Posso. Então não ponhas. Não pus. Tive 1 hora à procura do bug. E a formação foi para o galheiro. Por isso nunca mais me apanham nessas... Eu digo, não, isto funciona. De outra maneira, não sei. Logo se vê. Para isso?
Eu acho que é. O pessoal é chamado de que eu estava ali. Que é a segunda volta. Esse isso e eu vou estar a Vocês vão significar o que é compacta, que tem lá dentro o PSR, o serviço de e depois toma. Você não pode ter compacta, tem mais lá dentro. Você pode ter compacta. Aula não é. Você não tem. O PSR não é um tipo de Não está para começar. Já. É só porque eu percebo o objetivo. Isto são todos diferentes. Certo. E já vou fazer. Quando está para começar, é normal. Não é normal que eu. Isto é uma coisa complicada, porque depois da forminha, as aulas práticas depois chegam para o homem. Eu acho também que eu posso tentar. Não, está bem tempo para nós pensarmos e tentarmos e procurarmos, mas ao menos tem dizer uma coisa. Já. Mais 10 minutinhos, depois preciso, senão depois não vou ter acabar. Quando são propostas, não é só ser uma proposta, é ser proposta, não é de casa. Você tem que ir. Agora, não há que ir. Só não vai ter que
Eu tentar fazer o launch do seu. Tentar fazer o launch do seu cara.
Ai, não. Sim, nós PSR, você não tem este local. Sim. Eu acho que seria. Vamos ver se é lá desse mundo lá para
Eu estava a dizer que acho que as transformações do TF apareceu antes, portanto, um pouco.
porque agora apareceu aí que eu vi por exemplo, quando se instala o mas é tudo ao respeito, ponto, e não nos acontece. Assim, das informações que é ponto.
Horas, a ver se. Ainda 5 minutos. Ainda tenho 5 minutos para agoniar. Quer dizer, para fazer. Okay. Se calhar então vou começar, malta, senão depois não vou ter tempo de acabar. Okay, então deixem-me... in English. So let me get started so I have time to finish. So the first thing I will do is to create a new package. Let's call it... So we go to part 11. Catkin create package. So let's call it PSR 22 P2 part 11 exercise 6. Okay, then it's dependent on ROS by, ROS CPP, STD messages, and TF perhaps as well. Not sure if this is necessary, but Okay, so now we have a new package, which is here, okay? For now, it's empty, it has nothing there, but we can start by creating an URDF folder. That's where the URDF files go into, so URDF folder, and inside I'm going to create a file called scada.urdf, right? Okay, so we have an empty URDF file for starting, and now I'm going to create just something very minimal, just so if I can bring up the pipeline that I've told you about. So if I look here, I can see the URDF tutorials. And we have here the building a visual model. That's the first one. Well, we can pick up this example, okay? So our robot name will be Scada. Scada. Here we are defining links. So the coordinate systems. The first one is called base link. The second one is called right leg. And then we are defining a joint to put together two links. So the main components of the URDF files. So URDF stands for Universal Robot Description Format. So it's a way of specifying your robot kinematics in a file, an XML file. And the two major elements are links, which are coordinate systems, and joints, which are ways of putting together or articulating coordinate systems, okay? So in this example, we have the base link and the right leg and something articulating both. We can take a look at how this works by bringing up all the pipeline that I've told you before. So how can we do it? So I'm going to start from the end to the beginning, okay? So the end is, well, first host core, of course. Then RVs. RVs, I will make it go to the right, to the left. Then new tab. We know that we are going to need to read the parameters, the URDF file, into a ROS parameter. This is done, as you can see in the instructions, like this. Here, okay? So this instruction, ROS param set, you know what it does? It sets the value of a parameter, slash robot description, that's the name of the parameter. That's a standard in ROS. So this parameter will contain the description of our robot, and then quotes, and then some other type of quotes, which I don't know how to say. And then you write ROS run chakra scada.urdf. What this means, ROS run chakra, is that we are going to process the URDF file, and the result of this processing will be the value of the parameter. So if I go to my new package, so PSR 22 P2 part 11 exercise 6. Now I go into my URDF folder, and if I run ROS run chakra, and now the name of my URDF, which is SCADA, the output will be this. So this is just a way of processing the file, and this that I've highlighted now is what is going to go inside the parameter. So in order to run this code, I need to be in a place where the SCADA is. So I have first to ROS CD PSR 22 P2 part 11 URDF. Okay, now I can do this. So look, ROS param list. Very few parameters. After I run this, ROS, well, let me hide this for now. ROS param list. Now I have a new one, robot description, ROS param get, robot description. Here is the value of the parameter, okay? It's the contents of the file. So first part is done, to pick up the chakra, the URDF description and put it in a parameter, ROS parameter. Second part, we are going to launch the robot state publisher, ROS run, so clear perhaps, ROS run, robot state publisher, that's the name of the package, robot state publisher, that's the name of the executable. They have the same name. It's running, okay? That's it. Last but not least, we have to launch the joint state publisher, the one I told you that is needed in order to publish joint values. ROS run, joint state publisher, GUI, joint state publisher, GUI. So this will launch this special application, which for now has nothing. And it has nothing because of one particular question now here, which is, I'm only able to move joints which are dynamic. In the case of my robotic system now, if you take a look at the URDF, it contains a single joint, which is here below, and which is fixed. So because it's fixed, there's no joint to move. That's why my window has nothing to do, okay? In any way, what this means is that the transformation between the base link and the right leg is static. If it's static, then robot state publisher does not need a joint in order to compute its value and will immediately publish its value. So we may be able to see it here. So we have here the TF display, and now we just have to make sure that we are in the base link, okay? So here you can see that we have the base link and the right leg in the same place. Now, for example, if I go to my URDF and I say that my joint, okay, let me just do something here, has an origin. So if I add this field origin to my joint, I will define, it's not just origin, I think. Yeah, origin contains also an RPY equals 0, 0, 0. Okay, so this origin will define how the two bodies or coordinate systems connect to each other. In this case, if I say that they will connect on x equals 1 meter, it means that we will connect the right leg after 1 meter along the x-axis, counting from the base link, which is the parent link. So if I do that, now what I need to do is to bring everything down and then back up. So I changed the scar.rdf, so I need to load it again. Robot state publisher needs to read the new parameter, and now it's working. Okay, so you can see here the base link is connected to the right leg, but the right leg is further away. Diga lá, José. Okay, that's it. Okay, so now it's working. Well, what can we do now? We can add some visual components. You can see here that inside the link, we've defined what are visual components. The first one being a cylinder and the second one a box. So these visual components, we can see them in RVs if we add a special display type, which is robot model. So we can go to add robot model, and then when we put it there, we can see the visual components that we've defined in the URDF. So this is the cylinder, that's the box. For example, suppose that we want to make the box wider or longer. We can go into the box parameters, and this is the length in X, Y, and Z. Let's say that it's double the length in X. Now we need to shut it down, back up, oops, sorry. We need to load the parameter once again, load the robot state publisher once again. And now we need to take this away and put it here so that it updates. Okay, so, and it's working. Now we have a longer box. Now, one thing that is not working very well, you know that for me to do the SCADA, I will have to go to the URDF, change things, see the result, and do this over and over again throughout the next hour. Therefore, one major advantage is if I can do this process of shutting down, bringing up, bringing back up, and shutting down this one, bringing back up. If I can do it faster, I would save a lot of time or use it to better, use it in a better way. So I have to create a launch file, right? So let's create a launch file to launch everything of all this. And then we will fine tune the RDF once we have this launch file. So what I'm saying here, when you have an exam, question number 1, question number 2, when I was a student, I never started with question number 1. I would read them all and then start wherever I thought was easier. And this is the case here. If you start doing the ORDF, so if you do the whole exercise 6 until the end perfectly, you will spend 2 hours. In the end, for sure, you will make a mistake. Well, not one, about 100. But if you do just a little bit of exercise 6, let's say just with 2 links, then you go and do exercise 7. That's the robot state publishing. Then you go and do the way to put it, how to put it on the launch file. That's the way to go. So first you should do until 9 and then go back to 6 and do it better. Okay. So exercise 8 already has an example of how we can launch the robot state publisher and so on and so forth. So let's copy it. If it's a launch file, it must be in a launch folder. Launch. Let's just call it bringup.launch. Okay, here it is. Now, GUI, that's not needed. Parameter, robot description. So it's creating a parameter robot description, which is read. Look, when I do this, RCD, PSR, T2, P2, Arc11, okay? When I do this, ROS run, Chakro, and then I do SCARA, it's what I'm doing here with this command. It's the same. So ROS run Chakro, that's where I say find Chakro. That's just searching for the Chakro, for the place where Chakro is. For example, I could do something like this. ROS PWD Chakro. So where's Chakro? Oh, it doesn't exist. ROS CD PWD. Yeah, but this is different. Okay, no, don't forget what I'm saying. I'm just saying this is equivalent, not straightforward, not direct. There are some changes, but it's equivalent to launching the Chakro of the SCARA.ordf. So this was from last year. Before they had the .py, now they don't. And here we just have to put the model. So where is the model? Where is the SCARA.ordf? So the SCARA.ordf is in package PSR 22 P2 blah blah blah. So I'm going to find the path of the package PSR 22 P2 part 11 exercise 6. Then I'm going to jump inside URDF. Then I have the model called SCARA.urdf, right? So this is equivalent to what we were doing here. ROS param set blah blah blah. It sets the parameter appropriately after the URDF file. Then we can launch the joint state publisher GUI. We are using the GUI. Yeah, go ahead.
And then
the complete path, the hardcode. Yep. It works. When will it not be the same? Do you know? So you have to wait for Roberto to ask your code to copy. When he wants to copy your code, in his computer, your path is not valid. So it will not work on his computer, right? Yeah, right. So that way it will work. But this is more, how to say, more, it's general, right? Yeah, it's general because this part here will find wherever your package is, it will find it. Now, joint, that's it, okay? So now we can do, so with Basically, all this row on the left, we can do it automatically now. So we still have RVs. Now we just have to do ROS launch, PSR 22 P2, part 11, bring up. Oops. No such file directory. I made a mistake somewhere. Scara.urdf. I think it's here. PSR 22 P2, part 11, ex6 / urdf. UDRF. Well, URDF. Oh, yes. Let's try again. Oops, not yet. Robots, it doesn't know. Well, before, a while ago, it was called state publisher. So you did robot state publisher. So now you do ROS run, robot state publisher, robot state publisher. That's the name of the package right here and the name of the executable right there. Before, some years ago, you would do robot state publisher. You would do ROS run, robot state publisher. And then here you would do just state publisher. The name of the executable was different for some reason. That's why here the type was also different. But now we adapt and we put here robot. Okay. And that will be equivalent to what we were doing. So now we can try again. Up and running, okay? So, o que é que mudou? Era este robot state publisher. O pacote chamava-se robot state publisher, mas o executável chamava-se só state publisher. Agora é também robot state publisher. Sim, como temos no nosso, mas no guião está mal. Olha aqui, o guião tem isto mal. Exercício 8. Ok? Next, we want to launch also RV. So let's just bring up the whole system, not just some part of it. And that whole system includes RVs. So we can launch RVs, as we can see on exercise 9. So here, I will copy and then explain. So what are we doing here? First, we are defining an argument, which is just a variable. So we are not going to change this argument. We are always going to use the default value, which is the following. I have a configuration file in RVs that will allow me to how to say, have always the same configuration. So I don't have to, again, import a robot model and some TFs and change the fixed frame. All this is saved, which is great because we save a lot of time. So for that, I need to, in my package, create a config folder. And in this config folder, I will put my rvs.rvs file. And so this line here is launching the RVs. And when I say -d, then I have to put here my config file. So I can just put, I think it's easier if I do, yeah, PSR 22 P2 part 11 /r/config. And then our file is called rvs.rvs. For now, we don't have it, but that's okay. First time it will create one, and then we will add on top of it. So if I launch this again, I will also launch RVs with a configuration file that right now does not exist. So shut everything down, including the ROS core, everything down. And now we are going back, just ROS launch, exercise 6, bring up. Okay, here goes RVs. So I don't know why. Where? Here? Aqui? Aqui no find, né? Yeah, obrigado. Following package was not found. Find PSR P2 parte 11. Exercício 6. Okay, right now, I think still the RVs is the default one because we don't have any, because it didn't exist. So recent configs, I just wanted to reset my configuration, but I can't. Okay, let's say this is RVs is, okay, no worries. So let's just save this configuration as, and now we have to search for the place where I have my config folder. So this is in home, Catkin workspace PSR, source, PSR, part 11, blah, 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 config. And here I'm going to write RVs, .rvs I don't need because it already adds the .rvs extension. So now if I delete the marker array, the laser scan, the marker, and the point cloud, and I save, and I run it again, RVs is already configured. So the things that I deleted are not there anymore, okay? Now, the fixed frame is not correct. It should be base link. And now I save. If I delete and run again, it brings up everything, okay? So that's the way to work. You have to the best of your possibilities, to speed up your development, your test and test and see the result, test and see the result. These iterations must be as fast as possible. Otherwise, your project will start stalling. Okay, so now that we have a way to bring up the system very rapidly, now we can think of improving the URBF because we can test it immediately afterwards. So no launch file needed anymore. Here's the URDF. So now let's start adjusting for the case of the SCARA robot. So now we go back to exercise 6. Okay. So we have a base link, and then we have a link 1, and we have a rotation. So that's going to be a revolute joint. So the first is called base link. The second is called link 1. Was it? Yeah, link 1. So let's replace right leg by link 1. And here the joint name, I always call it by convention. It's also the ROS convention. The name of the parent link underscore 2 underscore the name of the child link. Okay. The type of the joint, it's not a fixed joint, it's a revolute joint. So it's called continuous. Continuous is a revolute joint that can rotate over and over and over, like a motor. And the parent link is the base link, the child link is link 1. Now, the origin will be on 0, 0, 0, and we need something else in order to define a revolute joint, which is, we need to define the axis about which the rotation is occurring. If you take a look at the drawing, you can see that the rotation axis is this one, the blue one, so the Z. So we need to say that it rotates about the Z axis. And this is done, I know how, but I don't know the exact syntax. So I just want to search for it. It's axis. No, perhaps it's not here. Building a movable, perhaps here. So axis, yeah, here, okay? So we are going to define that this revolute joint is going to operate around the Z-axis. 0, 0, 1 is 0 for X, 0 for Y, 1 for Z, okay? If we do this, notice that now we have a different robotic system because we have a joint which is dynamic and not fixed. So if we start the system once again, you can see here that we can, now we have access to one joint, which is the base link to link 1. And if we move it, so does the coordinate system and the body associated with it, right? We can actually go here to the robot model and add some alpha. Perhaps not so much. Okay, that way it's easier to see. Also, something else that we can try to do is to put some color. So we can go here and search for material. No material here, okay. Visual, yeah, I think here we have material. Yeah, material girl. This is a Madonna song, right? Perhaps you don't even know who Madonna is.
Yes.
Okay, so we are defining a new material, which is the color blue. And we can define some other materials. Let's say, oops, underscore. Okay, so let's define what we have here in our, so yellow, blue, red, green. So let's start with yellow. Yellow is this and this. Blue, red. So red we have here. So I'm just changing the RGB color codes. And green. Wow. Why am I going to red, green, blue? I'm following the order of the, yeah, I'm following the order of the drawing. Here. Okay, so we have several materials, and now we can say that this base link is supposed to be yellow, so we can say that it has the material yellow, like this. Okay, so material yellow. Okay, now the other one, the one on top, is going to be the blue one, right? So let's say that the material of the second link, the link one, is going to be blue. Okay, now if we launch this, okay, so we have a yellow and a blue one, okay? Next, what do we need to do? You can see here from the URDF that the coordinate system of the link one is higher. So it's on top. Let's say, for convention's sake, I say that this is 0.1, 0.5, okay? So let's say, or let's say 0.3. So let's say that height is 0.3 and that this height is 0.3 as well. So if I want to go from here to there, I need to add in Z 0.6. So this joint here will have an origin in Z of 0.6. And don't forget, I said that this height here is going to be 0.3. So I have to change the name, the size of the visual components. So this cylinder will have a height of 0.3. The radius is more or less half of it, so let's call it 0.15. And with regards to the link one, it has the same height, so it's going to be 0.3 in Z. The rest I'm not really sure about. Yeah, let's use it like this. Perhaps here. Okay, let's try. Are you following my reasoning? Yeah? Okay. Okay, so the coordinate systems are in the proper place. You can see the base link and the link one, they are where they should be. Of the box, yeah, of the blue box. So where do we change that? We change it here. So when we put the geometry, we can also tell, so whenever you draw a box, the coordinate system of the box is the center of the box. And you didn't want the center to be the coordinate system, we wanted the bottom of the box. So you have to subtract half its length. I'm in the wrong place. It's here in the box. So this is the origin. I think you can add an origin to the visual component here. You can see here. The visual component also has an origin. In this case, the box is this one.
I think you will have to do
the cylinder,
Because the same thing is also in the same.
Right. Yeah, you're right. So origin here. So in terms of rotation, I have 0, 0, 0. In terms of height, I have in this case 0.6, right? No, minus 0.3, I think, because I have to go back 0.3. I'm never sure if it's minus or plus. Let's see if it is. If not, it's the opposite. No, okay, that's it in terms of height. And now in terms of length. No, in terms of height, that's not it, because as you said, Enrique, that one needs to go down. So, yeah, first let's put the yellow one in the proper place, in the basis. So we have to define here an origin. And the length is 0.3, so this should be 0.15. I think, yeah, so now the yellow will be okay. No, the other way around. Minus 0, plus 0.15. Okay, now, yeah, now the base link is okay and the yellow is okay. The link one is okay, but the blue box is not okay. It should go up. You think? The height is 0.15. Yeah, right. I agree. Let's see if it works. That's it, okay? Now, well, not it. Now we need to make sure that the box moves to the right. So that means a displacement around x of half its length. So 0.8 exactly. Well, either 0.8 or minus 0.8, I don't know. Do you want to bet a coffee? You want to bet a coffee? Are you sure? Let's see. Wait, I did something wrong here.
You left an extra 0.
Okay. Okay, Jose, right. Makes sense. Okay, now we have to do the other one. So now, the other one will be better like this. Will be link 2. So we define a new link, which is link 2. If you take a look at the drawing, let's just say it's the same height, but with smaller length. So let's say instead of 1.6, it's just 1 of length, which means that this will be 0.5 probably, and the material is red. Okay, and now we need a joint. So let's replicate this joint. It's going to be from link 1 to link 2. That's the name of the joint. Then parent is link 1, child is link 2, and the origin, I think it's 0, 0, 0. And it rotates about the x, the z. Yeah, let's see. Okay. No, link 2 should be all the way up there. So we have to move it forward in the x direction. So this origin for this joint is x equals the length of the second link. That means 1 meter. Here, this 1 meter there. Okay, we can try it now. Yeah, the length of the link 1, not link 2. So it's half of 1.6. That means it's not here, sorry. Diga? Sim. This file here? No, this is just. Oh, does it have a new RDF example? I don't know. I don't remember. Where is it? That's because I already did it. For this morning's class. That's just a copy of this morning's class. I did a different example. I just came up with did a different explanation. I didn't follow the script so much. I was getting confused here because it was half of link 1 and half of link 1. Link 1 is 1.6. So here it should be 0.8. Is it? I'm lost. The full 1.6, that's it. That's it, Miguel, not half, the full. Nice. So now we have this, and if you take a look at the joints, we have two joints. We can move the first, and then we move the second. Now, do this in MATLAB. See how long it takes. You can do it. I did it a long time ago, but it's a different animal. Ross simplifies a lot of stuff. That's what I mean. Now, all we need to do is to do the final link, which is the end effector link, which will go up and down. So a new link. The end effector link. So this end effector is also a cylinder. If you take a look at the drawing, it's this green cylinder. So we copy here from this cylinder and we replace the box by a cylinder, right? So the length of the cylinder is much smaller than this. So let's say 0.5, well, not here, 0.5, and well, the cylinder should be 0.3, or perhaps, let's say 0.9, or 1, it's easier to do the math, okay? Now, the origin of this cylinder here, I think we just have to replace the Z, half of the Z component. I'm never sure if it's plus or minus. José, isto é menos ou mais? Aqui. Já está com o meu. That's cheating. That's what I do. I show, I see, and then I know which one is. See this one? Okay. I honestly don't know, so I'm positive X. Okay, I will put positive X, X or Z? Z. Z, okay. Positive Z, but Z is going up there. It's this coordinate system, not the other one. The answer I wanted from you is, I don't know, might as well show. Yeah, that's the proper answer. Yeah. Wait, did something wrong? But we need a joint for the link, of course. So this one is a bit trickier because of several things. The first one is that it's not a continuous joint, it's a prismatic joint. Well, for now, let's just say it's fixed, okay? So let's suppose that this is fixed and it will connect link 2 to the EE link. Link 2 to the EE link, right? And now, in terms of X, Y, Z, we have to go the length of the second link. So that means the length of the, I don't remember the color, which is now only 1. Sorry? 1, right? Yeah. And still, the movement is not rotating around the Z-axis, but it's a prismatic movement along the z-axis, okay? So axis should also be 0, 0, 1, although for now it's just fixed. So let's see how it results if we do it like this. I think it's good. Look, you can see here, well, let's change the color of the component to green. So this EA link is green. Okay. There it is, a green one. And it looks fine. What is not, from the drawing, what is not correct?
The origin.
The origin. So the origin of the coordinate system EE link should be the bottom of the cylinder, not the top. So how do I change that? I think it's just here.
Yeah.
No, I think it's plus instead of minus.
Yeah.
Okay, that's it. Now, something else is different, which is the coordinate system should be with x pointing down. Okay, and in this case, well, let me bring it here. In this case, it's with x pointing forward. So we need to do a rotation so that x points down. Now, this rotation will be, if we rotate around the y-axis, we will rotate to point the axis down. So I think that in this joint, we can rotate. So rho pitch yaw pitch rotates about the y-axis. And if you rotate 90 degrees, that means 1.57 radians, either plus or minus, I never know. I think it should work. Let's see. Yeah. Okay. Yeah. The axis. So the red, that means the x is pointing down. Now, our prismatic joint is not going to be along the z-axis. It's going to be along the x-axis, right? So now we need to change this for x instead of y. I think. Although this green object is still along the z. I think the green object is still along the z. Yeah, I need to rotate the visual part, which is here. I also need to do a rotation here of 1.57, I think, on the visual component of the EE link. Let's see. Oops. Okay. Not sure.
Yes, it's you are saying it's 0.5.
Mm-hmm. Ah, right. So now it's yeah, right. So now it's in another component, which we are not really sure which one. Not sure. Let's put 0 there, see what happens, but I'm not sure. I'm lost. Okay, 0 works. Ah, no, but now we need to go up on X, right. That's what you were saying, Miguel, I agree. So now it's 0. What's the length? 0.5, yeah. Or minus 0.5. Jose, you want to say? Good answer. Good answer. It's the other way around. Minus. Okay, now yes. Now, all we need to do is to create the prismatic joint. So for the prismatic joint, it's as simple as doing, instead of fixed, this is going to be prismatic. But because it's prismatic, I can't go all the way into the infinity and beyond and then go back. So I need to set the limits. So prismatic joints are required to have limits. And I have to search prismatic. Well, let me search. Cross URDF prismatic joint. So I have to set up this. So limit effort, I don't know what it is. Velocity, also not important. Lower, that's the minimum value of the joint. Let's say that it can go down 0.5 meters, negative, and go up 0.7, positive. Well, actually, go down is forwarding, so positive is there. So I would say that the negative is a positive value of, let's say, 0.1. So that the minimum that it can be is a little bit with the green inside the red, okay? Because we've changed the visual component so that the cylinder is moved up. It's here. When Miguel said something, it's this part. So first we rotated, and when we rotated the visual component, so the green cylinder was placed upwards. Then we wanted to, if we didn't do this 0.5, I will take it away so you can see. The cylinder would be in the middle.
Why is that?
So you see it in the middle, right? It's that's just because that was not the drawing. So the specification was that we wanted the reference system to be in the bottom of the cylinder. No, look at the drawing. It's on the bottom part. Yeah, right. So that's why we did this. And that way we can replicate more accurately what's happening in the drawing. So I think finally we have everything we need. And we can play with our new robot by moving this joint, then the other, and then finally a prismatic one. See? So this really results in something very nice. And you may say, oh, this is just some very simple stuff. Will it work for more complicated stuff? I can show you something. Okay. Just so you can see that it can work for much complicated stuff. Oh, not here. I had some drawings here. Where were the drawings? Yeah, here, look. You can see here a real FANUC moving. And you can see the whole robot being represented using exactly what I'm teaching you now, okay? It's not URDFs, it's chakras, but you will know what they are. So this is very powerful. It can really draw very complex stuff. I have other examples, such, for example, as the, well, MMT-bot or LRCC, but MMT-bot I can show you. So I had to define a chakra for this complete system. The table, on top of the table, I have the base of the manipulator, then the shoulder, then the elbow, then the wrist. Then connected to the table, I have a tripod, which has a camera and a LiDAR on top, blah, 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 blah. So I can even show you the URDF. So URDFs are typically placed always, I didn't do it now, but the convention is that they are placed on the name of the robotic system _ description. And then you have the URDF. And here is my URDF. Tables. Oh, where is my URDF? Not here. Well, I show you the URDF of the tripod. So a lot of stuff that you still don't know about, but the typical one. There is a link here. And there is a joint there. right? And there is another link here, and so on and so forth. Okay, so that's how you define. I can show you large CC. So for large CC, description, again, we go into the description. Well, first, what is large CC? Large CC is the system that you have up there on the laboratory of robotics. It's a gantry with several sensors and a manipulator in the middle. And so you can see it's a very complex system. I can show you a better example than this. Where? My problem is searching stuff. Okay, here. Examples. Okay, so here, an example. This is another example of an autonomous vehicle. So this is the URDF. Well, this is viewed in RVs, the robotic system of the Atlas car robotic vehicle down there. So you can see there is a coordinate system from each of the lidars near the bumper, and then for the cameras on the roof, and also for the vehicle, of course. This is a system with a camera, well, two cameras, one mounted on the hand effector and another outside. Here you can see the RV's representation. Agrob is a different vehicle from Porto. Again, you can see the RV's representation. Large CC is the one I was telling you about. It's something like this, okay? So you have the manipulator in the middle and then a big gantry. And here is the representation in RVs, all done using chakras and URDFs. This part of telling you, okay, this is not really a chakra, this is a new RDF. So what is a new RDF? Let me tell you. And that means that we are already in exercise 10. I will leave for you to try at home if you want. In exercise 11. So chakra files are files that are like an add-on to the URDF files. Because, for example, you've seen in this URDF file that I was doing something like the length X of my cylinder. So I define a cylinder, then I define my length 1.6. And then when I go to the visual, because I know that my length of the box is 1.6, I have to do the origin and subtract in X the half of 1.6. So here I put 0.8. This is really not very good for a programmer to work on. When this is very large, it's easy for you to get lost in so much detail. So that's one of the big problems of the URDF. You can't have any kind of variables or math. The chakra files, are very similar to RDFs. They are also XML, but inside them, you can define variables. So you could define a variable like L, which would be 1.6. And then here you would put L, and here you would put L over 2. And the system, the chakra, will do the math, okay? So chakras are better ways of defining your robot, very similar to URDF, but where you can have some additional functionalities for math and variables and macros, this kind of stuff, okay? But this part, exercise 11, I leave it for you to try at home, okay? That's it. I've spoken. I think that it's done. Do you have any questions? No questions? Okay, so be sure to work on the chakra, because what we will do in order to define a robot to do the final assignment. So the robot that goes around the house is going to be a turtle bot. Turtle bot. 3 waffle pie can be, okay. Not sure if I'm going to find the proper GitHub. Okay. So it has a description. It has an URDF. And there are several turtle bots. We are going to use the waffle pie. So this is the chakra of a turtle bot. It has several links. I can even show you turtle bot 3 waffle pie RVs TFs, something like this. I'm not sure if I can. Well, something like this without the R. Okay. So it's something like this without the arm. We can do the arm afterwards if you study a lot until January. But it's something like this. And what we will need in order for you to do the assignment, you will need to have a camera up here. Because if I tell you, go search for some object in the bed or on top of the desk, you can't be, so this robot is this tall. It's like an Achilles heel tall. It's very, very short. You need to create a structure which will support the camera, okay? So you are going to have to edit the chakra of the Turtlebot robot. So all of you will create your own robot per group, which will contain as many sensors as you'd like, and you have to define where they are pointing to. And then when you define a camera, I will tell you how you can extract an image from that camera. It does. It comes with a LiDAR on. So here it is. Yeah, this is simulation. It's zero cost. Well, nothing is zero cost in life. So this is a LiDAR, and the Waffle Pi I think brings a camera here. But again, this is not sufficient because it's only looking at the height of a very, very short, 20 centimeters or something. So you have to put additional sensors on top. The cost that you have is the processing cost. You can put 10 cameras, but then when you process them, it takes longer. Yeah, you can do this kind of jokes. Last year, did I show you already last year's competition? It was about hunting. So you had robots that were supposed to hunt other robots. And there was a student which did some claws. He would grab the robots, like hugging them. It was very nice. Okay, but this is also going to be very nice. If you can do it, it's going to be nice. So just to tell you why chakras are important. So study the chakras, otherwise you can't expand the chakra for the Turtlebot. Okay? Okay, see you next week. Bem, Henrique, você gostou desta aula ou o seu colega ou a sua colega enganaram?